Okay, let's come back to our class. So basically, in the last lecture, we have been talking about this problem of segmented least square problem. So this is, a very basic problem. In linear regression, actually, in general data fitting is basically want to consider approximating data points by a linear line. But basically, we want to have like a different generalization along this. And I guess this is basically like a showcase. I want to present that in general dynamic programming is very helpful in data science. And basically along this line, a very specific example we are actually seeing here is the segmented least square problem. That basically we want to consider maybe here a few different segments that you can actually approximate a few data points. And basically we want to make sure we want to have a good understanding about the places where we actually choose those segments. That basically here a key observation that we are going to we actually make here is that we want to consider. After all, we have like optimal solution, and after all, for the optimal solution, of course, it's going to have like a final segment. And basically, we have like a specific look at the last segment here. And basically, the last segments assume that it actually stop at the point I here. We know the corresponding cost then becomes Eij plus C plus OPT of I minus 1. So that is basically going to give us the result that we have this kind of OPT relationship that basically as long as J is larger than 0, it is going to be a minimum of Eij plus C plus OPT on I minus 1, ranging from all the i's between 1 and J minus 1 here. And basically for an algorithm here, we need to first compute all the values of the Eij's, and then basically we use this kind of unwind recursion idea that basically we can bring we can basically construct this M table from bottom up. Basically, we can iteratively basically compute this minimum here. Then finally, we return this Mn as our final output. Okay, so basically, is there any question for this general idea? For instance, this specific algorithm. I guess for this algorithm, probably the correctness is relatively straightforward. It's just, when we consider this kind of OPT here, this just very honestly follows the definition of being optimal here, and also the definition of the segmented least square problem. So the main thing that we need to analyze here is running time. So basically, for this algorithm, the running time. Actually, we need to take a look. There are basically two parts. So initially, we need to really compute all the values Eij here. And also on the other hand, we need to construct this M here. So basically computing all the EMJ here. Eij here. There are actually ON squared pairs. And each take ON cost. So that is basically seeing the overall cost. It's basically overall cost for computing. Maybe let me make this more clear. So the overall cost for computing Eij is then ON cube. On the other hand, computing all M. So what is the cost of computing all the M's here? So basically, for M0, this is just trivial. And in general, for MJ, actually needs to compute the minimum of J minus 1 values now. So the cost is then basically of 1 plus 2 plus until n minus 1. And this is actually ON squared. So basically for the segmented least square problem, the overall cost is simply ON cubed. And actually setting up is more expensive than dynamic programming here. Of course, this is not the case in general, but I think a point is that in general for the dynamic programming algorithm, you need to be careful about about like setting the algorithm and also running the dynamic programming. And actually, for the weighted interval scheduling problem, and basically for our algorithm, excuse me, excuse me. So basically, for this algorithm we gave here, so we also have the part of setting up the algorithm. Oh, sorry, not this one. This one. So we also have the part of setting up the algorithm, and then we need to run the dynamic programming. So as we just discussed, basically for sorting and computing, basically the cost is O n log n here, and running the dynamic programming only costs O n here. So actually, in general, I mean, if you want to consider algorithm using dynamic programming, I mean, you need to be careful in general about what is the overall time cost. I mean, maybe the setup is also quite expensive in general. And actually, this is the case for the segmented least square problem. The setting up is cost O n cubed, and actually the overall running time is only O n squared here. I mean, the cost of running dynamic programming is only O n squared here. Okay, so basically this finishes the discussion of the segmented least square problem. So is there any question about like the problem, the algorithm, and the time complexity analysis? Okay, so if there is no further question, I think I'm probably going to talk about the last problem that we are going to introduce today, which is the knapsack problem. So I guess in general, you probably see that basically for the problem, I mean, basically for we have this algorithm idea, basically greedy, divide and conquer, and then today we are introducing dynamic programming here. So I'm trying to introduce problem from a little bit different background. So for instance, like the Huffman's code, basically is a very important information theory problem. And I think we talk about a lot of graph problem and I think scheduling problems. So here for the knapsack problem, I think this in general can solve a lot of combinatorial optimization problem. So let's actually see what is a knapsack problem. So in general, you actually given n objects, and that's so-called like a knapsack. Okay, so we say item I has weights wi larger than 0, and actually also has values vi larger than 0. So the knapsack, I mean, your knapsack is definitely not so large, so it actually has a capacity. The knapsack has capacity of W. Here. And the goal here, I mean, you only have this one knapsack, and you know that knapsack has a complexity W here, and you have these objects. I mean, you have these objects. I mean, I from 1 to n, and actually they are corresponding have weights. I mean, W1, W2 until Wn have these values. So the knapsack is actually has like a limited capacity, and under this case, the goal here is that you want to fill the knapsack so as to maximize on the total value. So this is just the knapsack problem. You can just imagine that such kind of knapsack problem in general can characterize a lot of problems. I mean, in general, in discrete optimization or combinatorial optimization, they want to consider like whether you want to have something or not, etc. So this is a very standard problem, and maybe for instance, let's see an example here. So we are going to have some items, and these items are going to have values. Maybe not values, and weights. So let's consider a case where, for instance, n equals to 5 and w equals to 11. So we are actually going to have 5 items here. And we know the knapsack has actually a capacity of 11 here. So let's consider maybe these 5 items, they have the weights, for instance, 1, 2, 5, 6, 7. I mean, we could just imagine, for instance, these are like diamonds of different weights. So for instance, like a diamond of weight 1 has value 1. A diamond maybe, for instance, at weight 2 has like a value 6. And maybe, for instance, here, maybe let's say it's like 18, 22, and 28 here. So I guess this is just like some random instances maybe we can think about. So maybe in this instance, we clearly see that n equals to 5, and maybe let's think about the case where you only have a knapsack of capacity 11. What can you do here? So for instance, we consider the third item and the fourth item. So the third item and the fourth item, their total weight is actually 5 plus 6 equals to 11, and actually it is good. We can actually together put the third item and the fourth item in our knapsack. So this is good. The value is then 18 plus 22 equals to 14. So think about, for instance, this example. What is the best strategy that we can do? I mean, what is the maximum value that we can give for finding this knapsack? Or maybe in general, I mean, maybe not only for this specific example, what is like a good strategy that you can potentially use to fill up your knapsack here? So maybe let's say that, for instance, I mean, a very natural strategy is also greedy. I mean, in general, we are talking about like putting items into a knapsack. So a very direct way that you can think about this problem is that maybe, I mean, you want to put items that really, I mean, it deserves that value. I mean, but what does it mean by deserve such kind of value? Maybe, for instance, a good strategy is that you want to repeatedly add item, which maximize the ratio. Which maximizes the ratio Vi divided by Wi. I guess this probably makes a lot of sense. I mean, you want to think about what is the item you want to add. I mean, if an item has the largest ratio on Vi over Wi, this means that, I mean, according to, I mean, for instance, like the value per weight. I mean, this is basically the value per weight. And this is really, I mean, from this perspective, this is like a very good item that you want to add here. So, but for instance, if you have this kind of a greedy strategy, I mean, you add an item which maximizes the ratio Vi over Wi. What is the result of running this greedy algorithm for this specific example? So for this example, so actually 18 divided by 7 is actually 4, and actually 22 divided by 6. This is basically something like this. And basically for 18 over 5 is exactly 3.6, and 3 over 2 is actually 3, and actually 1 over 1 is just 1. So actually for this problem, this ratio, this I mean value per weight is actually increasing according to the weight of the problem. It happens to be that. But basically, if you have this strategy, so basically we then greedy, we need to first pick. I mean, basically we need to pick the last. We pick item 5 here. After we pick the item 5 here, the remaining weight is then become 11 minus 7 equals to 4. And basically, after picking the item 5 here, item 3 and item 4 here, they are not available anymore. And after that, I mean, we have weight 4 here, and we only have 2 items, and they are actually weight 1, weight 2 here. We can just after that pick both of them, item 2 and 1. So the total weight is actually 28 plus 6 plus 1 equals to 35. Actually, this is smaller than 40. Basically, if we choose the item 3 and 4. So this is saying that greedy is not optimal. So what is the intuition here? So basically for this knapsack problem, you can imagine that this in general, this greedy strategy, it should be something good, but it's probably not the best. I mean, especially for this hard instance, I mean, for this problem, it is just like after you pick the, I mean, if you pick the best item, I mean, it really has this largest BR over WI ratio, you pick this. The tail is really disturbing. I mean, basically after you pick the item 5 here, then the remaining thing is that you only have weight 4 here. You only have the freedom to choose item 2 and item 1 here. And actually, they are really of low quality, and even you actually even don't fill up your whole knapsack. And actually, because the summation of the total weight is only 1 plus 2 plus 7 is 10, you don't even fill up the whole knapsack. So although at the very beginning you pick up like a very valuable, actually the best choice at that moment, basically the tail, the remaining space, it is not of the best use. And basically, this is a main reason why this greedy is not optimal. And basically, although this sounds like a good strategy, maybe you want to build up some further strategies along this, and you want to have a good understanding about, I mean, what you can do beyond that, give an efficient algorithm for this knapsack problem. Okay, so any questions for this definition of the knapsack problem and basically this hard instance? Okay, so I guess you can probably see that this problem is really like a relatively difficult problem compared to directly using a knapsack, directly using a greedy strategy. So for this knapsack problem, I mean, we also have this number of items. Maybe you can still think about, I mean, using like a dynamic programming strategy for this. So for instance, maybe we can do a temp like this. So maybe we can define this OPT of I to be the max profit subset of items. I mean, still we need to have this kind of parameter. So here we just like go through all the items. I mean, 1, 2 until I here. I mean, there are also, I mean, some other situations that we, I mean, in general, we need to think about what is like all the possibilities. I mean, for instance, maybe we are currently at item I here. So case 1, OPT does not select item I here. I mean, for instance, I mean, you consider this OPT, I mean, it is ranging from item 1, 2 until I here. It may happen that it probably selects I here, or maybe it doesn't. So if it does not select item I here, then basically we know that OPT, I mean, because it is an optimal solution, it definitely selects best of 1, 2 until I minus 1. So for the second case, we know that the OPT is actually going to select item I here. So basically along this, we know that accepting item I, actually this is the case we will be a little bit more complicated. That basically, I mean, after accepting the item I here, I mean, basically the size of the knapsack is actually going to change. So actually the thing is that, I mean, issue that we are actually having here. I mean, I just want to discuss about, I mean, whether this is like a correct strategy or not. So issue is that accepting item I here does not immediately imply that we will have to reject other items. So this is a difference, for instance, compared to the weighted interval scheduling problem, because the weighted interval scheduling problem, we are talking about like the compatibility of intervals. I mean, after having, for instance, this ascending order according to the finishing time, having an interval, it is very clear that what are the intervals that we can pick and what are intervals that we cannot pick. But here, I mean, for the next step problem, it is not immediate. I mean, for instance, here I pick the fifth item here. I mean, you can maybe still pick some of the, I mean, after picking the fifth, it's probably immediately see that you cannot pick the third and the fourth, but how about the first and the second? And maybe, for instance, in some more difficult cases, I mean, maybe, for instance, like the W here maybe equals to 100. I mean, if it equals to 100, then probably just true, just pick all of it. But what if like W equals 12? After W equals to 12, you will clearly see that actually you can, in that case, you can pick item 3 here. But if W equals to 11, you cannot. But actually, this really depends on not only the value of I here, but also the value of W here that you can pick. So this is probably something we need to be careful about. So basically, this is not working directly. So at least, I mean, from a high-level perspective, we probably need more sub-problems. Okay, so this is basically saying that at least like a very first attempt, I mean, for instance, I mean, we just like following the weighted interval scheduling problem and also follow the this segmented least square problem. We maybe we just brute forcefully consider, I mean, this OPTI, OPTJ, but unfortunately, it is not going to work because, I mean, it is not transparent as transparent that we can give a direct relationship between OPTI and J here, because you probably need like more subproblems, especially maybe you need a parameter in terms of W. To characterize what is the specific problem that you are going to work. So the solution here, I mean, maybe let me use the red color here. So the solution here is, of course, also very straightforward. We need to add a new variable for the capacity of the knapsack. So here we are basically going to have this definition. So we define OPT of IW to be the max profit subset of items 1, 2 until I. Let me use red here. It's wait. So you see, like this is basically a nature that is significantly different compared to the to say, for instance, like the segmented least square problem. So here, basically for the segmented least square problem, we just consider, I mean, still the OPTJ here. We consider just like the range of the points here. So the original attempt here that basically, I mean, the original attempt here that we just consider max profit of subsets of item on 1 to 2i. This just is not going to work because we really need to have a good understanding about like the other parameter, that is what is the current weight limit. So this is basically something we need to be very careful about. But after having both parameters, I mean, basically we have like I think I made a typo here. I think this should be small w, because I'm using the small w here. So basically, we need to have a good understanding about what is the recurrence in terms of this OPTIW. Basically, having both parameters, what is the relationship we are going to have. So still, we are talking about basically the range of items from 1 to 2i here. So there are just two cases. We have this item I, or we just don't have the item I here. So we discuss accordingly. So case 1, OPT. Does not select item I. So in this case, we just know that OPT is actually going to select best of 1, 2 until I minus 1 using weight limit W. So how about the second case? At OPT selects item I. So in this case, the new weight limit is actually going to be W minus W. So basically, in this case, we know that after having that, basically we select item I here, then we got like a new weight limit. And the next thing is actually transparent, that we are going to know that OPT is going to select a best of 1, 2 until I minus 1 using this new weight limit. Okay, so is this clear to you? Okay, so I guess basically, I mean, still based on this case 1 and case 2 discussion, I guess we can make a recurrence now. So we know that OPT IW is actually going to equals to 0 if I equals to 0. And also on the other hand, OPT I minus 1 W. I mean, if WI is larger than W. I mean, if WI is larger than W, I mean, it is just, you just cannot select. You just go down here. And actually, we say that the new weight limit here is actually W minus WI. To make this make sense, it only makes sense that actually the W here is actually larger than, or maybe, yeah, I guess we probably don't, maybe we can write the quality here. I mean, sorry, probably shouldn't have that. Sorry for the confusion here. I mean, if your item I here is actually already, its weight is more than your current capacity of your current knapsack, you just cannot select item I. In that case, you just like go to the OPT I minus 1 W here. But on the other hand, I think basically for this case 2 here, I'm discussing about this new weight limit here. This new weight limit equals to W minus WI. I mean, to actually make this case 2 feasible and to make this make sense, we actually also need to have the other case. I mean, otherwise, to make the discussion make sense. But actually, for this case, I mean, if actually WI is smaller than W, we really need to be careful. And this is the case we need to make a comparison between case 1 and case 2 here. And in this case, of course, it's going to be the maximum between OPT I minus 1 W, and also because here on the other hand, we are actually choosing the ith item, and this is going to give you a value of VI, and then this is going to be the of OPT. So the item is still you finish the item I part, and basically you only need to focus on item from 1 to I minus 1 here. So the first parameter of OPT becomes I minus 1 here, and the second parameter becomes because the ith element is actually going to take you a weight of WI here. So the second parameter is going to be this. Okay, so is this clear to you? So this is basically the relationship that we are going to study for this knapsack problem. And I guess subsequently, we can just write down an algorithm accordingly. So the algorithm that we are going to use here, it is another bottom-up algorithm. So the input is going to be this n, and actually this W1 until Wn, and also V1 until Vn. Or I think at the very beginning, we need to have an input of capital W to represent the overall capacity of your knapsack. Okay, so let's now do the algorithm here. So the algorithm is that for n, I guess for W from 0 to capital W, we just write down m 0 W equals to. I guess this is just transparent. So if you don't have any item to choose, I mean, of course, the final value is going to be 0 here. So now, I mean, we really need to go through all the value of the i's here. So basically, for I from 1 to n here, we basically, on the other hand, we also need to have this recursion of all the W's here. So here it's just very naturally it's going to have you, maybe let me use the black color here. It is just very naturally you are going to have a double loops here. So for I from 1 to n here, and also for W from 1 to W, capital W here. So we are going to do this. So if this Wi is actually larger than your current W, if the Wi is already larger than your current W, it suffices that the value of IW equals to I minus 1 W. Because the item 1 is just not helpful. It is just like too much to take the weight compared to the overall capacity of the current knapsack. So else, so if we are running the else case, we know that actually Wi is actually smaller than W. We know in this case, we are going to have that MIW equals to the maximum of the I minus 1 W. And on the other hand, Vi plus I minus 1. And then finally, we are going to return and so it's this algorithm, basically the algorithm, bottom-up strategy of the algorithm based on this recursion cleared. Okay, so I think to have a good understanding of this algorithm, let's actually just do another copy and paste here. Let's do this. Okay. So let's consider a strategy that we are going to use maybe for this example, and basically let's think about what is the algorithm that we are going to have for this. So let's actually example. Maybe let me actually make this a little bit small here. It's long, I think we fine because I guess this is going to be, oh, excuse me. This is going to be a table that is a little bit big. So yeah, let's do this. So an example. So here we are going to consider something like this. So basically we draw some lines like this. So here is basically the value of small w, and here we consider the value of small I. And basically, for the value of small w here, we can have like a 0, 1, 2, 3. Oh, I need another line here. And for the i's here, at the beginning, we are talking about the empty set. I mean, we don't have any item, and we actually go from 1. All the items we cover 1, 2, and actually 1, 2, 3, and actually 1, 2, 3, 4, and actually 1, 2, 3, 4, 5. So maybe we can draw a table like this. So what is the result of running this algorithm? Let's do this gradually. So I guess here, I mean, after this lecture, I will definitely share you the lecture note, but maybe after you see the end of the lecture note, I mean, I just finished the table, but maybe if this is not totally clear to you, you can just check the recording. Hopefully this is going to be clear. But nevertheless, let's do this. So let's take a look at this table. So this basically, I mean, for the case where I is the empty set, basically the first line, we are basically looking at this, that M0W is going to be 0. I mean, you don't have any item to choose. It's just 0, 0, 0, 0, 0. I guess this should just be relatively straightforward. So basically, it goes to the next line. So for the next line, we need to be a little bit careful here. So basically, we first consider the case where actually this is going to happen. I mean, if Wi is larger than W, the Wi here, so basically W1 here equals to 1 here. And this is actually larger only under a case where this value, and basically for this value, just copy this. I mean, because just in this case, I mean, even the first item, I mean, although it has like a weight 1 here, but if you don't have any weight, this is not going to be helpful for you. So basically looking at this part, you know that the first entry of the table is actually going to be 0 here. But what about the next entry? So in the next entry, you already goes into this condition. That basically the W1 here, the W1 here equals to 1 here, and the W here is actually equal to 1. So you really need to consider like the maximum here. So basically, in this maximum, this is relatively straightforward because if you look at this, I mean, all the i's here is that basically you consider, nevertheless, all this, I mean, it is going to be something like M0W, but M0W is always 0. I mean, this is not going to bother you by much. You only need to worry about this part. So basically, this Vi plus M minus 1 of this M minus Wi. So you know that Wi actually it equals to 0 here. So basically, the thing that we are going to write here is that this Vi equals to 1 here. So you are going to write 1 here. But keep in mind, this 1 here is actually the value of V1 plus a 0. Which 0? This 0. Why is that? Because currently you're at the value where W equals to 1, Wi equals to 1. And that is actually going to be 0. It just happened to be this entry is 0, but actually it is 1 plus 0 equals to 1 here. And actually similarly, this value is also 1 here because this 1 here is actually still this 1 here, this V1 or plus this. But this actually currently it is then M01 here because you are currently have W equals to 2 and Wi equals to 1. So you're actually going to write here, basically you have this value to be 1 and this is always like 1 plus 0. It's just like the first lines. It's just so simple. So you can just feel free to write down. I mean, just similarly, I mean, all you have like these ones. I guess this should be relatively straightforward. But I mean, for the next line, it is going to be much more tricky along this. So let's see, for instance, what is the entries, I mean, for the next line. So still for the very beginning, I mean, it suffices that we take a look at this if condition here. I mean, if your item is just like it has too large weight compared to the current size of the knapsack, you don't need to worry about that. So currently the Wi here, so basically we are talking about W2 here. The W2 here equals to 2 at the moment. So if the W2 here, it is actually 2 here, you actually for the 0 and 1 case, you don't need to worry about that. And basically you just like copy what is have been written for the table above. So sorry. So that is basically saying you can safely write a 0 and 1. But you need to be super careful about what is the next entry here. So what is the next entry? So for the next entry, you basically you have go into this kind. Let me actually erase this. So you actually now go into this condition here because your W2 here, which is 2, is actually smaller than 2, smaller than or equal to 2 here. So now you actually you need to look at specifically look at this. So now actually especially for let me write down for instance like M22 here. M22 here equals to the max of M12 here, and actually the V2 plus M. And actually it is going to be 1. And here at the very beginning, W minus Wi is actually 0. So you are basically writing something like this. So what is the value that you are making a comparison here? So basically you are making the comparison between M12 here. So basically the M12 here, it is this value. And on the other hand, the V2 is actually the V2 here according to this table. The V2 here is actually 6. And M10 here is actually 0. And this part, M12 here is actually 1. But you clearly see that here 1 is actually smaller than 6. So we actually write a 6 here. So any questions at the moment? So let's now take a look at the next entry. So what is the value in the next entry? So for the next entry, we are basically talking about now M23 here, which actually equals to M13, and V2 plus M11 here. But actually this part changes because M11 now equals to 1 here. So this is going to be now the maximum of 1 and 7, and it is actually now 7 here. And after having that, I mean, for instance, if this goes to 4 and this goes to 4 and this goes to 2. But I mean, if you look at the later part, I mean, for this, M12, M13, M14, etc., they are all 1 here. So it never makes a difference. And we can simply write down 7, 7, 7, 7, 7, 7, 7, 7. So any question at the moment? Okay. So things becomes actually more and more tricky here. So let's look at the next line. So basically for the next line, basically, I mean, for this part, what is the case where actually W3 is larger than your W here? The W3 actually equals to 5 here. So you can just very directly, I mean, for when W equals to 0 to 4, you just copy the previous line. You just copy. Excuse me. You just copy this. But basically, now next you need to have a good understanding about what is the next entry. And the next entry, you're actually going into the next line. Basically, you are going to compute the maximum here. And actually for this maximum, what is the corresponding value here? So here, maybe let's just be a little bit cautious and let's write down this again. So the M of 3 of 5 here, it actually equals to the max of M3, M2, 5. With the value of Vi here, the Vi here is actually quite large here. It is actually 18 plus the M of the 2, and actually here it's actually 0 here. And actually M25 here, you just look up the table here. The M25 here is actually a 7. I mean the previous line. And actually this is 7 and this is 18 and plus like M20. The M20 here is actually a 0 here. And actually a clear observation here is that, I mean, for this part, I mean M25, I mean also for the later part until M211. This part is not going to change. I mean, if you look at, for instance, this is 2, 6, 7, 8, etc. But this part, I mean, this actually goes from 1, 2, 3, 4, etc. I mean, this part is, I mean, the second term is always larger than the first term. So actually, literally speaking, what you are actually doing here is that you are more like a plot. You're actually, I mean, for this, etc. You are actually plotting like 18 here along this. So basically, for this value, you have the first value to be 18 here. The next value to be 18 plus 1, which is 19 here. The next value is 18 plus 6, which is 24 here. And then it's actually 25. And because, I mean, always 18 plus 7 is always 25. So you just feel free to write down 25 here. So any question at the moment? Okay, so this is good for you. Okay, so let's then take a look at the fourth line here. So basically, the fifth line here, where I equals to 4 here. I mean, still at the beginning, we take a look at this. So basically, W4 equals to 22 here. Oh, sorry, what I'm talking about. So W4, I mean, equals to 6 here. The value of the fourth item equals to 22, but W4 equals to 6 here. So according to this, we can just feel free to write down, I mean, all of this. We just copy all of this to the next line. Again, we still need to be super careful about those. We need to be super careful about those. And actually, this is the part, again, we are actually going to take the maximum. But maybe actually we can think about what is the maximum we are going to make a comparison with. So basically, we look at the table. So always what we are making here, because basically we are talking about M-1W here. We are making a comparison between what is right in the line right above, and also the value of all this, plus the current item, right? So here, I mean, for this 0 here, you're actually comparing 0 plus 22 against this 19 here. So here you can just very much feel free to write down the value of 22 here. But what about the next value here? So this is actually a super tricky part because you have 1 here. But actually 1 plus 22 is smaller than 24. So this is the part, this is actually a specific place where actually the first item is larger than the second item. So here, I mean, this is not actually going to work because actually you have 1 plus 22 here, but it's actually smaller than 24. So you should really write 24. But after that, you are relatively good because you have like a 6 here. 22 plus 6 is larger than 25, and you just write down 22 plus 6, which is 28 here. And actually for this, 22 plus 7 is actually larger than 25, etc. So you just feel free to write down 29, 29, 29. So after class, please take a second think about why this value is 24. So this is actually the place where we need to pay specific attention with. Oh, I guess I only have like 3 to 4 minutes, so let's actually wrap up here. Let's actually also finish the last line. So for the last line, I guess we can just feel free to write down all of this. So this is basically because the weight of the 5th item is actually 7 here. So I mean, whatever until 6 here, we just like copy everything down here. And actually similar to what we are talking about previously. So basically for this part, and basically for what is above here, we are actually comparing, for instance, here, like 0 plus 28 over 24 here. So we feel free to write 28 here. But for this entry, we are actually still considering like 28 plus 1, 28 plus 1 until this 28 here. So we are actually going to have this, we are going to have like a 29 here. And actually, for this value, we are actually comparing this 28 plus 6, which is 34, compared to this 29 here. So we can just feel free to write down this is actually a 34, and actually a 35 and a 40. And actually, after having this, we know that OPT is actually equals to 3, 4, and actually the value. So for this knapsack problem, it is not so difficult, I mean, to find a solution. It's just, you just use the same strategy using this that is already used in this weighted integral scheduling. You can use like a find solution strategy. Sorry, understand. You just run you can just run a find solution, I mean, to actually find a solution with the same time cost. In general, I mean, as long as, I mean, in this recursion, it is smaller than what you are currently having, you just like discard. And if it is actually matching the strategy here, just output that. So basically, finding this optimal solution here is not a big problem. And actually, we can clearly see that the overall running time here, because taking the maximum is not really a big deal because we're taking the maximum among two numbers here. So we can clearly see that the running time is actually O of n times W. So we actually need to make a remark here. Remark here is that this actually depends on inputs. So for most algorithms we have been talking about, I mean, we talk about algorithm that depends on like M and N here. So it is actually case independent because, for instance, I mean, graph problem, as long as you have like a graph with N vertices and M edges, you have this time. But here it is clearly saying that actually the time cost should be depending on the W here. Actually, if it's not dependent on W, maybe our first attempt, I mean, basically this attempt, it does not depend on W, but does not work. So this is not going to be so helpful. So actually, we should say that this is depends on inputs. And furthermore, I mean, this is actually, I mean, in terms of W, this is not polynomial in the input length. I mean, if for instance, if the dependence is only polylog in terms of W, I guess in general it is tolerable because they have this way of encoding the problem. I mean, it's like zeros and ones. It is, for instance, like it's like a polylogarithmic in terms of W, which is going to be a polynomial in the input bit length. It is probably fine. But this is just like a linear dependence in W. I mean, for instance, your knapsack is too large. I mean, for instance, if the knapsack is, you only have a few items, but the knapsack is a million size. So this is not so good. Let me actually finish in another like 1 or 2 minutes. So this is called a pseudo polynomial. I mean, this NW dependence is called a pseudo polynomial time algorithm. And in fact, the knapsack problem is actually NP complete. And actually, in later part of this class, we will introduce what is NP complete in our lecture. I just want to make sure that this is actually a very difficult problem. And in general, for the knapsack problem, it is, I mean, I won't say it is impossible, but as far as the current knowledge of human, people don't know how to give an algorithm that only have like polynomial dependency M and also polylog dependent, at most polylogarithmic dependent in terms of W. This is not. But nevertheless, I mean, just for the knapsack problem in terms of dynamic programming, we have this algorithm which calls O of N times W. Okay, so any quick questions for this knapsack problem? Basically, this finishes the introduce to the. Okay, so if there is no question, I guess we have finished the lecture today and see you next week.